Hello students, welcome back to session 12 of Hilbert spaces class. So in this class we will discuss about the finite dimensional spectral theory. So first let us begin with the definition. Suppose T is an operator on a Hilbert space H. Then a scalar lambda is said to be an eigenvalue of a transformation or a operator T if there exists a non-zero vector x in H such that T of x is equal to lambda times of x. Okay. So if T is an operator on a Hilbert space H, then a scalar lambda is said to be an eigenvalue. Lambda is an eigenvalue of an operator T if there exists a non-zero vector x belongs to H such that T of x is equal to lambda times x. Okay. Also, if lambda is an eigenvalue of T, then any non-zero vector x belongs to x H such that T of x is equal to lambda times x is called the eigenvector corresponding to the eigenvalue lambda. Okay. So these type definitions you have already studied in your linear transformation class. Let us take up few results related to this now. So among them, first one is, say, if T is a normal operator on a Hilbert space H, then an x is an eigenvalue of T with eigenvalue lambda if and only if x is an eigenvalue of T star with eigenvalue lambda bar. Means if T is a normal operator, then x is an eigenvector if and only if x is an eigenvector of T star with eigenvalue lambda bar. Okay. So let us prove this now. Now as T is normal, you know that T is normal means T minus lambda times I is also normal, because I is also normal. So linear combination of these two normal operators, definitely it is normal, because I is normal means lambda times I is normal, T is normal means T, and lambda times I is normal means, so the sum is also normal for any scalar lambda. Now consider T minus lambda I whole star. This can be written as T minus lambda I whole star is T star minus lambda into I star, lambda bar into I star. So this is equal to T star minus lambda bar into I star is I itself. Okay, because adjoint of I is I itself. But we have proved one result which says an operator T on a Hilbert space H is normal if and only if norm of T star of x is same as norm of T of x. Okay. Here, since T minus lambda is a normal operator, therefore according to above result, norm of T minus lambda I of x is equal to norm of T minus lambda I whole star of x. This holds for every x belongs to H. This happens if and only if T minus lambda times of x under norm is equal to norm of T star minus lambda bar I of x for every x belongs to H. So this happens if and only if T of x minus lambda of x is equal to T star of x minus lambda bar of x holds for every x belongs to H. You call this as number 1. Now from 1, so we can conclude that as T minus lambda I of x is 0 if and only if T star of x minus lambda bar of x is 0. So we can say that T of x minus lambda of x is 0 if and only if T star of x minus lambda bar of x is 0. Now T of x minus lambda of x is 0 means what? X is an eigenvector of T corresponding to eigenvalue lambda. Now T star of x minus lambda bar into x is 0 means yes, x is an eigenvector of T star with eigenvalue lambda bar. Thus x is an eigenvector of T with eigenvalue lambda if and only if x is an eigenvector of T star with eigenvalue lambda bar. Okay. So this is one result. Next, suppose T is an operator, normal operator on a Hilbert space H, then the eigenspace of T, the eigenspaces of T are pairwise orthogonal. Eigenspaces of T are pairwise orthogonal. So for this, let M1 and M2 be two eigenspaces of a normal operator T on H corresponding to the distinct eigenvalues lambda 1 and lambda 2. Okay, so M1 and M2 are the eigenspaces corresponding to the distinct eigenvalues lambda 1, lambda 2. So what we have to show? We have to show they are orthogonal. Okay, so means M1 is orthogonal to M2. For this, let's choose x1 belongs to M and x2 belongs to M2. x1 belongs to M1 and x2 belongs to M2. Now x1 belongs to M1 means x1 is a eigenvector of T, means there exists a as x1 is an eigenvector of T corresponding to the eigenvalue say lambda 1. Therefore, T of x1 is equal to lambda 1 x1, and x2 belongs to M2 means, so M2 is the eigenspace corresponding to the eigenvalue lambda 2. Accordingly, T of x2 is equal to lambda 2 x2. Therefore, we have lambda 1 into inner product of x1 comma x2 is equal to, so inner product of lambda 1 x1 comma x2, that's equal to T, lambda 1 x1 can be written as T of x1 comma x2. Now we transform T to this side, it becomes T star. So x1 comma T star of x2. So this is equal to x1 comma T star of x2 is lambda 2 bar x2. Okay, so T star is lambda 2 bar x2. So lambda 2, if you take it outside of the inner product, it becomes lambda 2 into x1 comma x2. Therefore, lambda 1 into x1 comma x2 is equal to lambda 2 into x1 comma x2. Therefore, lambda 1 minus lambda 2 into inner product of x1 comma x2 is 0. This implies since lambda 1 lambda 2 are distinct, lambda 1 minus lambda 2 cannot be equal to 0. Therefore, inner product of x1 comma x2 is 0. Inner product of x1 comma x2 is 0 implies x1 is orthogonal to x2. Thus, x1 is orthogonal to x2 for every x1 belongs to M1 and for every x2 belongs to M2. Therefore, we can conclude that M1 is orthogonal to M2, means the eigenspace corresponding to the eigenvalue lambda 1 is orthogonal to the eigenspace corresponding to the eigenvalue lambda 2, means eigenspaces are pairwise orthogonal. Okay. Next one, let's take up the other result. Say, this result says, suppose T is a normal operator on a Hilbert space H, then the eigenspaces of T reduces T. The eigenspace of T reduces T. So now let m lambda be the eigenspace of T corresponding to the eigenvalue lambda. Now we show that m lambda T reduces as m lambda reduces T. M lambda reduces T, okay, means what? We have to show that m lambda is invariant under both T and T star. M lambda is invariant under both T and T star. Now, as eigenvector is non-zero, because eigenvector means non-zero vector. So, as eigenvector is non-zero, definitely at least one eigenvector belongs to m lambda, and so m lambda cannot be equal to 0, means it is non-zero space. But x belongs to m lambda happens if and only if T of x is equal to lambda times x. Also, clearly 0 vector is in m lambda. Okay. Therefore, if 0 vector is in m lambda means 0 vector definitely satisfies the equation T of x is equal to lambda times x. Okay. So therefore, m lambda is equal to set of all x belongs to H such that T of x is equal to lambda times x. So set of all x belongs to H such that T minus lambda I of x is 0. Now set of all x belongs to H, T minus lambda times of x is 0 means what? This is nothing but the null space of the operator T minus lambda I. Okay, null space of the operator T minus lambda I. Now, yeah, therefore, null space of T minus lambda I means it is, you know that it is a subspace of H. Already shown that. Range and null spaces are subspaces means m lambda is a linear subspace of Hilbert space H. Again, since T and I are continuous, okay, they are operators. T is operator, I is also an operator, means they are continuous linear transformations. So they are operators means they are continuous. So T minus lambda is also continuous. Now, but null space of a continuous linear transformation is closed. This we have proved earlier. Null space of a continuous linear transformation is closed. Now T minus lambda is continuous and null space, this is m lambda is nothing but the null space of the continuous linear transformation T minus lambda I. Therefore, according to this result, m lambda is closed. Okay, m lambda is the eigenspace, m lambda is a closed space. Now let's come to the actual proof of this theorem. Say yes, first we show m lambda is invariant under T. Okay, we need to show m lambda is invariant under both T and T star. So first we show m lambda is invariant under T. Let x belongs to m lambda. X belongs to m lambda means by definition what will happen? T of x is equal to lambda of x. And look here, x belongs to m lambda means any scalar multiple of x also belongs to m lambda. Okay, because m lambda is a linear space, means according to that lambda times x belongs to m lambda for any scalar lambda by definition of a linear space. Now lambda x belongs to m lambda means lambda x is nothing but t of x. T of x belongs to m lambda. Thus x belongs to m lambda implies t of x belongs to m lambda. Therefore, you can declare that m lambda is invariant under T. Okay, m lambda is invariant under T. Now we show m lambda is invariant under T star. So for this, let x belongs to m lambda. Then T of x, again T of x is equal to lambda times x. This implies T star of x is equal to what? Lambda bar of x. Again, x belongs to m lambda implies any scalar multiple of x belongs to m lambda. Let us say lambda bar into x also belongs to m lambda. But lambda bar into x means t star of x, means t star of x belongs to m lambda. Thus x belongs to m lambda implies t star of x belongs to m lambda. Then by definition what? Yes, it implies that m lambda is invariant under t star. So m lambda is invariant under T as well as m lambda is invariant under T star. Therefore, we can conclude that m lambda is invariant under both T and T star. Consequently, by definition, m reduces the operator T. Okay. So m reduces the operator T. Now we are going to prove the important theorem of this section. So this is stated as the spectral theorem. So it states, if T is an operator on a Hilbert space, on a finite dimensional Hilbert space H, and if lambda 1, lambda 2, etc. lambda m be the distinct eigenvalues of T, and m1, m2, etc. mm be the corresponding eigenspaces, and let p1, p2, etc. pm be the projections on these eigenspaces. P1, P2, etc. Pn are projections on these eigenspaces, means the range space of P1 is M1, range space of P2 is M2, and so on. Okay. Then the following statements are equivalent to one another. The first statement is the MIs. Okay. The eigenspaces are pairwise orthogonal, and these spans the Hilbert space H. First one. Second one says the PIs are, okay, the projections are pairwise orthogonal, and the sum of these projections P1 plus P2 etc. Pm is equal to the identity operator, and T can be written as lambda 1 P1 plus lambda 2 P2 etc. lambda m Pm. Okay. So second says the projections are pairwise orthogonal, and sum of this projection gives the identity projection, and T is the linear combination of these projections. Third one is T is normal. T is a normal operator. So we need to show these three statements are equivalent to one another. Okay. So but already we have proved few important results. So let us state one by one. We have proved if P and Q are projections on closed linear subspaces M and N of a Hilbert space H, then M is orthogonal to N. M is orthogonal to N if and only if PQ is 0, if and only if QP is 0. Okay. if m is orthogonal to n, okay, if and only if pq is 0, if and only if qp is 0. And also we have proved if p1, p2, etc. pn are projections on closed linear subspaces m1, m2, etc. mn of Hilbert space H, then p is the linear combination of these, not sum of these, p, the sum of these projections p1, p2, etc. pn is a projection if and only if pi's are pairwise orthogonal. And in this case, P is a projection on M, which is the sum of these subspaces M1, M2, etc. Mn. This result also we have proved. Okay. Third one, the third result says if P is a projection on a closed linear subspace M of a Hilbert space H, then M reduces an operator T if and only if Tp is equal to Pt. Okay, because T and P commutes each other. If P is a projection on a closed linear subspace M of a Hilbert space H, then M reduces an operator T if and only if Tp is equal to Pt. So we name these three results by 1, 2, 3. Okay. So let us come to prove the required result. Say first one is, let us assume 1 and you prove 2. 1 implies 2. Suppose mi's are pairwise orthogonal and this spans H. And this spans H. Okay. Then now mi's are pairwise orthogonal and this spans H means any vector x belongs to H can be written as a linear combination of sum of these spaces. Means x belongs to H implies x is equal to x1 plus x2 etc. xn, where each xi is an element of mi. Okay. So you call by this number 1. Now they were given my's are pairwise orthogonal. Then by result 1, if mi's are pairwise orthogonal, then pi's are pairwise orthogonal. Okay, result says m and n of Hilbert space H are S, then m is orthogonal to n. Okay, so first result says m is orthogonal to n if and only if the projections are pairwise orthogonal, pq is equal to 0. So accordingly, what will happen, as mi's are pairwise orthogonal, by result 1 the projections pi's are pairwise orthogonal, that is pi into pj is 0 if I is not equal to j. Now if x belongs to H, then for each I, pi of x means p1 of x, p2 of x and so on. Pi of x is equal to pi of x means what? x1 plus x2 etc. xn. So this is equal to, since pi's are linear, pi of x1, pi of x2 etc. pi of xi and so on, pi of xn. You call by this number 2. Now look here. Now xi belongs to mi, which is the mi means what? Range space of py, because m1 is the range space of p1, because p1 is a projection on m1 means what? m1 is the range of p1. Similarly, m2 is the range of p2. Therefore, what will happen? If xi belongs to the range space of pi means what? By definition, pi of xi is xi itself. Okay, this is by definition of a range of a space. So further, if j is not equal to I, definitely mj is definitely orthogonal to mi, because these spaces, these are orthogonal to each other. Now since xj belongs to mj, look here, xj belongs to mj, therefore as mj is orthogonal to mi, xj is orthogonal to mi for each I. Now xj is orthogonal to mi means where xj belongs to? Xj belongs to the dual space of mi, so which is mi perp. Mi perp is nothing but what? Null space of pi. Yeah, if mi is the range space, then mi complement is the null space of pi. Now xj belongs to the null space of mi means what will happen? Null space of pi means pi of xj is 0 if j is not equal to I. If j is not equal to I. Thus pi of xi is xi and pi of xj is 0. Pi of xj is 0 if I is not equal to j. Then what will happen? So then from 2 what will happen? So from 2 says pi of x is pi of x1, pi of x2 etc. pi of xn. Therefore from 2 pi of x on the left, pi of x is equal to what? Pi of x1 is 0, Pi of x2 is 0, etc. Pi of xi is xi. Other terms gets cancelled or becomes 0. So we will have from 2 Pi of x is xi. You call by this number 3. Now for each x belongs to h, we have I of x can be written as I of x is x itself, but x is what? x1 plus x2 etc. xm. Now x1 can be written as, according to this, p1 of x is x1, p2 of x is x2 etc. pm of x is xm. So instead of these I can write it as p1 of x, p2 of x etc. pm of x. So this is equal to p1 plus p2 etc. pm of x. Means I of x is equal to this much, means I becomes I is equal to p1 plus p2 etc. pm. One condition we have proved, p1 plus p2 etc. pm is equal to I. And also for every x belongs to h, we have t of x can be written as t of x1 plus x2 etc. xm. Since t is linear, this can be written as t of x1 plus t of x2 etc. t of xm. T of x1 is what? Lambda 1 x1, lambda 2 x2 etc. lambda m xm. So this is equal to lambda 1 into p1 of x1 can be x1 can be written as p1 of x plus lambda 2 into x2 can be written as p2 of x and so on, lambda m into pm of x. So x is common, so this can be written as lambda 1 p1 plus lambda 2 p2 etc. lambda m pm of x. So what is on the left? T. T of x is equal to lambda 1 p1 plus lambda 2 p2 etc. lambda m pm of x means what? T becomes lambda 1 p1 lambda 2 p2 etc. lambda m pm. So thus we have shown p1 plus p2 etc. pm is equal to I, and t is lambda 1 p1 lambda 2 p2 etc. lambda m pm. So we have proved 2. So 1 implies 2, right? So next let us assume that 2 and let us prove 3. 2 implies 3. So what they were given? Just now we have proved t can be written as lambda 1 p1 lambda 2 p2 etc. lambda m pm, where each pi's are pairwise orthogonal, we have assumed. Now since p is a projection, what will happen? Pi star is pi as well as pi square is also pi. Also they are pairwise orthogonal, means pi into pj is 0 for I is not equal to j. Okay. Now let us consider t star. Okay. T star is what? Lambda 1 p1. T is lambda 1 p1 plus lambda 2 p2 etc. lambda m pm means t star is lambda 1 p1 lambda 2 p2 etc. lambda m pm star. So we take adjoint lambda 1 bar into p1 star plus lambda 2 bar into p2 star and so on, lambda m bar into pm star. So this is equal to what? Lambda 1 bar into p1 star is p1, lambda 2 bar into p2 and so on, lambda m bar into pm. So consider t into t star. T is lambda 1 p1 lambda 2 p2 etc. lambda m pm into t star is lambda 1 bar p1 etc. lambda m bar pm. So you multiply both these two, you get lambda 1 into lambda 1 bar is lambda 1 square into p1 is p1 square. Next is lambda 1 into lambda 2 bar into p1 into p2 is 0. Therefore all others get 0 except mod lambda 1 square into p1 square plus mod lambda 2 square into p2 square etc. mod lambda m square into pm square. So this is equal to lambda 1 square into p1 square is p1 etc. lambda m square into pm. So now t into t star is this. Similarly we can show that t star into t is also the same. Therefore t into t star is same as t star into t. T into t star is same as t star into t means t is normal. Okay, we have shown that that operator t is normal. This means 2 implies 3. Now finally let us take up 3 implies 1. Okay. Suppose that t is a normal operator on a Hilbert space H and the eigenspaces mi's are eigenspaces of t. Now mi's are eigenspaces of t means what will happen? Then mi becomes pairwise orthogonal. We have proved this. Mi's eigenspaces are pairwise orthogonal. So one condition we have proved, mi's are pairwise orthogonal. Therefore, and it remains to show that, okay, mi's span H. mi's, these eigenspaces spans the Hilbert space H. Now mi's are pairwise orthogonal and pi's are projections on mi's. pi's are projections on mi's which are orthogonal means pi's are also pairwise orthogonal by the result 1. Okay, m is orthogonal to n if and only if pq is 0, means pi's are pairwise orthogonal. Okay, let m be the sum of, let m1 plus m2 etc. m. Okay, then by result 2 what will happen? So m is a closed linear subspace of H. M is a closed linear subspace of H such that P is P1 plus P2 etc. Pm is a projection on M. Okay, M, if you take M as the sum of these, then M is a closed linear subspace such that P is a projection on M. Okay, this we have proved. Okay, now since T is a normal operator on H, therefore each eigenspace Mi of T reduces T. So since T is a normal operator, therefore each eigenspace Mi of T reduces T. Just now we have proved in this class. Okay. Also Pi is a projection on the closed linear subspace Mi of H. Okay. Therefore Mi reduces T if and only if Mi reduces T if and only if Pi of T is equal to T into Pi. Pi of T is equal to T into Pi by the result 3. Therefore, T into P becomes T into P means P1 plus P2 etc. Pm. So, this is equal to T into P1, T into P2 etc. T into Pm. So, this is equal to P1 into T. Okay, because T into P1 is same as P1 into T. So, PQ is same as QP. So, this is P1 into T, P2 into T etc. Pm into T. So, this is equal to P1 plus P2 etc. Pm into T. So, this is P into T. So, T into P is equal to P into T. Now, P into T is equal to T into P and P is a projection on M. Then by again result 3, according to result 3, what will happen? M reduces T. M reduces T means what will happen? M reduces T if and only if M bar S, M orthogonal complement of M is invariant under T. Is invariant under T because M reduces T implies M bar is invariant under T. Let U be the restriction of T to the subspace M lambda. Suppose you restrict the operator T as U to the subspace M lambda. Then what will happen? Then U becomes an operator on a finite dimensional Hilbert space M lambda, and U of x is same as T of x for every x belongs to M lambda, because U coincides, T coincides with U or U coincides with T, or T is equal to U on M lambda. Okay. Next, if lambda is n, look here, if lambda is an eigenvector of U, if lambda is an, if x is an eigenvector of U corresponding to the eigenvalue lambda, then x belongs to M lambda. Okay, x belongs to M lambda, and as U of x is equal to lambda times x, and then x belongs to M lambda and U of x is equal to lambda into x implies T of x is also lambda times x, because for for the elements in M lambda, U is same as T. So U of x is equal to lambda f x implies T of x is equal to lambda times x, and so x is an eigenvector of T. So if x is an eigenvector of U, then x is also an eigenvector of T, means all the eigenvectors of U are also eigenvectors of T. But T has no eigenvectors in M lambda, since all the eigenvectors of T are in M. Okay, and M intersection M perp is always contains 0 vector as common vector. Therefore, U is an operator on a finite dimensional Hilbert space M lambda, and U has no eigenvector. U has no eigenvector means what? U has no eigenvalue. U has no eigenvalue means therefore we must have M lambda is equal to 0. m lambda is equal to 0. But h is the sum of m plus m lambda. M lambda is 0 means h becomes n. So h is equal to m means what? m1 plus m2 etc. mm. Now h is the sum of these subspaces means these mi's spans h. Okay, understand now? So we have proved these mi's spans the Hilbert space H, which is the condition 1 which we need to prove. So we have assumed that T is normal. Okay, we have assumed that T is normal and we have shown that mi's are pairwise orthogonal and spans the Hilbert space H. Okay, so these are the few results for this class. Okay, thank you for listening.